Okay, so I'm back. So today we're going to do the worksheet for modeling curves of best fit rather than the linear ones. So this one we actually have to determine which polynomial will be best. It could be a straight line, it could be a quadratic, it could be cubic. So I'm going to turn them all off. You just look at the R squared values for these previous ones here. So here hotel rooms are charging, over 200 rooms charges $120 per night and has all the rooms occupied. For every $10 increase, 5 rooms are decreased. So let's go put this in here. So 1, 2, 3, 4, 6. Okay, so those are increases of $10. So they're like $60 there at the very bottom there. Okay, and then the revenue they make is going to be less each time because you keep on losing. But actually, it goes back up here. So it starts up high, goes down, and goes back up, and goes back up even higher. Oops. We should put all the zeros in there and all the 8s as well. Okay, 2, 9, 7, 5, 0, and 3, 2. Okay. Seems like they're always making money here. So the Y values are gigantic, so we're going to have to zoom out of my graph here quite a bit. Well, so I'm just holding shift down, grabbing the axes, and you can see that there's a slight little curve to this graph here. Now I want to know which regression is the best regression to use here. So the R squared for a linear is actually pretty good, but you notice the R squared for my quadratic and my cubics are 1. They're perfect. So I'm just going to go with the easiest one. I'm going to go with the quadratic here. You can see that fits the data nicely. So it looks like I'm going to be using a quadratic here. No, sorry, just 1 second. Put that in the marker. I'm going to go with the quadratic version of this. Okay. Using the regression model, determine the equation. So I got my equation here, I got my A, my B, my C, so it's AX squared. Revenue, so let's call this R rather than Y. So this is like my Y value here, so I'm going to call that R. And this is my X, so I'm going to call this cost, C or something, who knows. Or increases, or I's, or I'll just call it X. I don't care. Let's call that X. Okay. So negative 50x squared. I don't know why I put that in parentheses. I don't have to put that in parentheses. Then plus bx, and my b is 1400 plus the c, which is 24. Perfect. Okay. What's the maximum amount? So maximum amount. So I'll go here, just click on the graph. If you click on the graph, you can see that there's a gray dot there. You just click on that dot. I'll tell me my maximum amount, and my Y value. So $33,800. How many rooms will be occupied at this price? So remember, X is, well, actually, I don't know how many rooms. Every time I increase by X, I have 5 fewer rooms. So this is 14 increases. So we'll write that down. 14 increases means 14 times 5 less rooms. It's 14 times 5. 70. So 70 rooms are going to be, yeah, so there's going to be 70 rooms less than 120. So again, minus 120. So 120 rooms. Is it 120 or is it 200? Oh, it's 200. I'm sorry. So it's 200 minus the 70. This is a pretty tricky question, actually, when you think about it. So 130 rooms occupied here. Oh, it's a bit tricky. Model rocket being launched here, so let's double figure out what we're having here. So we got heights and we got some times. So I get 0, 1, 3, 8, 14, 20, and 25. Okay, awesome. And then 3, 148, 410. I'll put my market thing down here. 90, 140, or what? Not 100, 1,140, 1,025, and 700. So everything matches up there. Looks pretty good. Go down here, look at our R squared values. It looks like, ooh, the cubic one is the best of the cubic ones here because it's 999. The 4 nines rather than 9997. So I'm going to say this is going to be cubic. Okay. Now the equation is a little bit trickier. I'm just going to call this x and y. Y is equal to the nearest hundreds, so 0.02x cubed, so that's ax cubed, plus bx, b is negative here, squared, then plus cx, plus d. There you go. Based on the equation, total time. So I'm going to look at this equation. Where's my graph here? It looks pretty good. Just pull that out a little bit. Zoom here just a bit. We're using the cubic one here. So let's use the cubic one. So I'm turning the cubic one back on. Can't really see it go back up, but this is my graph right here. So it looks pretty good. Based on the equation, what's the total time to intercept the rockets in the air? So if this is height, it's in the air from 0, time 0, all the way to time 31.1, because it wants to do the nearest 10th here. So that's 1 decimal place, 31.1 seconds. So this is like the x-intercept. The height is equal to 0. Right. Maximum height. You can see here, I'm going to highlight, there's a little gray dot there, so I'm going to hit that gray dot. And then you notice the maximum height is 1,000. 1 to the nearest what? To the nearest meter. 40 meters at time is equal to 15.2 seconds. I believe it's in seconds, right? Time seconds, yeah. Nearest 10th of a second, what time is the rocket 1 kilometer in the air? 1 kilometer is 1,000 meters. So I'm going to put 1,000 meter line here. Oops, sorry, I'm going to put a y is equal to 1,000. There you go. So what time is the rocket 1 kilometer in the air? So it's in 2 spots here. Remember, it goes up and then it comes back down. So the times that's in the air to the nearest what? To the nearest 10th of a second is 9.8 seconds. And if I go over to the other side here, 20.7 seconds. What's a good appropriate domain here? So my domain, yeah, we'll just use x's again. 0, 2, and what do we say the max time was here is 31.1. When it hits the ground, so I don't think we need to care about time after that. Okay, my range, which is my height, well, I'll just call that y for now, goes from 0 to my max. What did we say my max was? So 1,140. There you go. Okay, so we got one more here. So we're going to do another regression. This time a metal detector or something. A motion detector. What am I thinking? So 0, 4, 8, 12, 16, and 20. 205, 295.7, 224.0. Cool. Now we want to determine which is the best of these R squareds. And you look at the R squareds here. Obviously cubic, these other R squareds are horrible. So cubic again. Okay, so that put the cubic line on, because you can see the other ones, they don't match at all. It doesn't match at all. This doesn't match. But the r squared here is 1, so that's the best. My equation, I'm going to use t and d this time. Yeah, so my d is my output here. So ax cubed, so it'll be d cubed, or t cubed, sorry, minus 9.05 t squared, because that's the b squared one, cx, so plus, and then plus d. So there's my equation for that one. Okay, so using the regression now, after 24 seconds, what distance would the mechanic expect that the distance separating the motorcycle from the sensor would be? Okay, so at 24 seconds, let's find 24 seconds. Now, if I wanted to create a vertical line, I can just drag this along, wait till I find 24 seconds. Probably could do that. Let's see, there's 24 right there. That's 742.4, but I can also put a line here, so I can x equal to 24, put a nice little vertical line, and there's my dot there. So the distance I would expect this to be, because the d is my y values, this is my y values. These are my x values, right? So 742 to the nearest what? To the nearest meter, 742. Cool. How far away from the motor detector when it is close? Oh, at its closest point. So it starts here at starts here at 200.5. It goes up to 295 or 296, and it goes down to, this is probably the lowest point right here, 70.8. So it's just the lowest point, the minimum point of my graph here. And the other mechanic is standing at 210 meters away from the, at that time. At that time, expressed to the intercept is the motor. At what times is equal distance from the motion detector? Okay, so I'm going to put a, we have a distance here, so that's a y value. So I'm going to put a 210. And you can see that there are 3 times where this motorcycle's at 210 here. So it's at 210 when time is equal to, I'll put d is equal to here. When time is equal to, wait, I want this to the what, nearest tenth? 1 decimal place then. 0.2, 8.5 seconds. And the last one here, they all say it's 210, 210, they all have 210 there. And equidistance just means the same distance. 19.5 seconds. So all those times there. Okay, hopefully that helped you out. I'll see you in the next video. Bye.